Welcome back to Math 104. Our task is to find the exam grade cutoffs for a C and a D. We already know that the cutoff for a B in points is 73.65. We also already know that 22% of the class plus another 24% of the class, that's 46% of the class, have already been accounted for. That leaves 4% of the class above the mean and in the C range. And since the C range consists of the next 30% of the class below the B range, that means that there's another region just below the mean, running from the mean to somewhere, containing 26% of the class. To find out where that somewhere is measured in standard deviations, we look inside the table and try to find something equal to or very close to 0.26 as one of the entries. When we do that, it turns out to be 0.71 standard deviations away from the mean. In this case below the mean. Since the 4% just above the mean receive C's, and the entire next 30% of the class below the B's receive C's, that leaves 26% that are just below the mean, who also receive C's. That means a region from the mean to somewhere that we'll call negative Z that contains 0.26 of the class. Thus our job, in order to find Z, the number of standard deviations below the mean that gives us the lower bound for a C, in order to find that Z, we have to look inside the table and try to find 0.26 or something very close to it as an entry in the table. That turns out to be approximately 0.71. Thus the cutoff exam score for a C, the lower cutoff, equals the mean minus 0.71 copies of our measuring stick, which equals 68.385. The next 15% of the class, that is the next 15% of the class down from the cutoff for a C, receives a D. That means there's some region here just below the C range that contains 0.15 of the class. It runs from 7.1 standard deviations below the mean to some negative Z, that is Z standard deviations below the mean. But we should not be looking up 0.15 in the table. If we look up 0.15 in the table, that will tell us about a region that runs from the mean down to somewhere containing 15% of the class in a sliver right next to the mean. Instead, it is a different kind of region we're studying. This Z has a total of 41% of the class between the mean and it. We need to look up 0.41, the sum of 0.15 and 0.26. We need to look up 0.41 in the table and see what Z score corresponds to it. This turns out to be 1.34. Our cutoff for a D is 1.34 standard deviations below the mean. In points, the cutoff for a D is the mean minus 1.34 copies of our measuring stick, and that is a 64.29. And now we are ready to tie it all together. How is the binomial model related to normally distributed data? Experiments whose outcomes can be represented as words in a two-letter alphabet have been important throughout this course. For example, flip a fair coin 10 times. If we note the number of heads obtained in 10 flips, an ideal dataset for this experiment has the following histogram. The height of each rectangle represents the probability of, for example, exactly 5 heads, or exactly 6 heads, exactly 7 heads, exactly 8 heads. Finding any one of these probabilities is a job for the binomial model. These experiments and the probabilities of events related to them have been with us throughout the course. This image is from a wonderful website hosted at Berkeley. You may find it useful to go take a look. The histogram here is just the arrangement of rectangles. This bell-shaped curve is just superimposed on it. We have commented before that these histograms look roughly bell-shaped. In other words, this is a key point. The ideal datasets for such experiments, the ones that the binomial model is related to, are approximately normally distributed. I can take the histogram for such an ideal dataset, and I can draw some kind of a normal curve that approximates it. But here's a really key point. There is one specific normal curve most closely associated with this histogram. If there's one specific one, then which normal curve is it? It's the one with the same mu and sigma as the histogram for the ideal dataset for the coin flipping experiment. What does that mean? For a normal curve, there's a notion of mu, the notion of population mean. But for these binomial experiments, these sequences of n independent Bernoulli trials, there's also a notion of mu. There's also a notion of the mean. The mean of an ideal data set is the same thing as the expected value. And when the experiment consists of n independent Bernoulli trials, that expected value, that mean, is exactly n times p. We also have a nice formula for the standard deviation, square root of n times p times 1 minus p. If I already have a particular coin flipping experiment, or an experiment observing the birth order in a family in terms of boys and girls, or observing the ups and downs of the stock market, or asking a group of people, are they in favor of a certain law or are they against a certain law? I can take the mu and sigma from that experiment and draw a normal curve based on exactly that mean and that standard deviation. For the experiment of flipping a fair coin 10 times, the one we were just looking at, find the mean and the standard deviation of the corresponding normal distribution. This experiment has a certain mu. It is given by mu equals np, that's the formula. N is 10, p equals 0.5, so the mean is 5 heads. Right, that makes sense. You flip a fair coin 10 times, on an average run of that experiment, you get 5 heads. What about the standard deviation? The formula is sigma equals square root of np times 1 minus p. N equals 10, p equals 0.5. So we get the square root of 10 times 0.5 times 0.5. That's the square root of 2.5, which is approximately 1.5811. So of all the normal curves out there, we know exactly which one corresponds most closely to our experiment. The one with mu equals 5 and sigma equals 1.5811. That's nice. Now what do we do with it? Now use the normal distribution with the mean we just found, 5, and the standard deviation we just found, 1.5811, to compute approximately the probability of the following event. There are exactly 5 heads in 10 flips of a fair coin. Don't worry, you're not supposed to have already known how to do this. We're going to see how it works now. This normal curve, which was drawn with exactly mu equals 5 and sigma equals 1.5811, closely approximates the histogram for the ideal data set for our experiment. How does that help? The amount of yellow paint here is a certain fraction of all the paint that's inside the histogram. Whatever fraction of all the paint inside the histogram is yellow, that's the probability of our event, 5 heads in 10 flips. That's the geometric way of thinking about probability when you represent the experiment in this visual way. In terms of the normal curve, the mean is right here down the middle, and there is some interval that runs from some negative z up to positive z when you measure it in standard deviations. How do I compute how much this z is? How far above the mean this location is right here along the horizontal axis above the mean? Just in terms of how this horizontal axis is labeled, look what number appears here. This spot at the tip of the arrow is right between 5 and 6. Right? 5 represents the entire yellow rectangle. So the 5 marker along here is right in the middle of this rectangle. It's in the middle of this interval. I want to understand what are the endpoints of this interval. So the upper endpoint of this interval is actually 5.5. And that 5.5 lives a certain distance above the mean. I want to divide through by the standard deviation, and when I do that, it turns out that this is approximately 0.32, which means that negative z here is negative 0.32. In terms of the normal distribution, if we pretend that we're dealing with continuous data so that 5.5 actually makes sense, and 4.5 actually makes sense, this location at the tip of the other arrow is 4.5 along the horizontal axis. So from 4.5 to 5.5 is, in standard deviations, from negative 0.32 up to positive 0.32. In terms of the normal distribution, that has a certain probability. This sliver to the right of the mean, but still painted yellow, has probability 0.1255. When I go look up z equals 0.32 in the table, I obtain 0.1255, which means that the other side of the yellow rectangle, this sliver to the left of the mean, but still painted yellow, also has probability 0.1255. Our conclusion? the probability of 5 heads in 10 flips is approximately equal to 0.1255 plus another 0.1255, which is 0.2510. That is just an approximation. We already know an exact way of finding the probability of the event in yellow here, but now we have another way of computing it approximately. If we painted in all the area underneath the curve and looked between negative z and positive z and asked what fraction of the area under the curve lives in this region, it would come out to be 0.2510 of the total area under the curve. Now, that's just an approximation, and we can ask how good an approximation is it? The exact probability when we compute it is 10 choose 5, p to the 5 times 1 minus p to the 5. Probability of heads raised to the number of heads times probability of tails raised to the number of tails, and that equals 0.2461. The normal approximation gave us 0.2510. That is not bad. The only way to master this is to practice it. So before going on to the next video, use the normal distribution with mu equals 5 and sigma equals 1.5811 to compute, approximately, the probability of the following event. There are at least 6, but at most 8 heads in 10 flips of a fair coin. And here is the histogram with the appropriate events highlighted in yellow. In particular, you have to think, what is the address of this point along the horizontal axis, and what is the address of this point along the horizontal axis? Think what those are in terms of the scale from 0 to 10, and then convert each one into a z-score, a certain number of standard deviations above the mean.